Hi. Now, we've been examining the sequential circuits. What we have done already is the general representation of sequential circuits. That was the general representation of sequential circuit. It's combined with the combinational circuits and the memory elements. And then we modeled these sequential circuits, how we modeled them. There were three models: a mathematical model, state table, and state diagram. Now we are going to come inside this memory element. So in this slide, we will be examining memory elements. How we are going to examine memory elements? Here we are, memory elements. There are two groups of memory elements: latch memory elements and flip-flop memory elements. When we come to the latch memory elements, the first thing that we are going to see is the fundamental memory elements. Fundamental memory elements are the ones from which we can introduce all the other memory elements. Therefore, they are called fundamental memory elements. So in this video, we will be examining these fundamental memory elements. Let's go inside. So escape from here, move that up, and open board, and we've got to switching to open board. Okay, here you are. So that's the fundamental memory element, and is SR memory element. It is called. S comes from set, R comes from reset, set. So definition relation of this the output is as you know, each state variable, that is mathematical variable, is represented by one memory element. So that means each memory element has got one state variable. That is the state variable. Why we've got small y and capital Y? We are saying small y is independent variable, capital Y is the dependent variable, and small y shows us the present state, and capital Y shows us the next state. So here you are, it is written here. So for example, let's examine this one. If the present state is 0, that means your memory element present state is 0. You applied input 0, 0. Your next state, which is capital Y, so inside is the capital Y, becomes 0. That means no change, isn't it? If your initial state or the present state is 1, if your input is 1, 0, 0, then your next state is 1. That means your state is not changing. So if you interpret this first column here, for the 0, 0 input, state do not change. If it is 0, stays as 0. If it is 1, stays as 1. So if you look at the second column here, if the input of this memory element is 0, 1, that means S0 and R1, whatever the present state is, the next state is 0. That means next state Y is independent from the present state small y. Similarly, if the input is 1, 0, whatever the state you are in, either 0 or 1, your next state is definitely 1. So what it means, if your input is 1, 0, the next state do not depend on the present state, small y. So if you look at this 1, 1 column here, make it different color, pay attention to that. It says KK, the meaning is that is a forbidden input. Forbidden input. That means you should not apply this input to that element. What happens, I will explain in details later on, but this is an input that must not be applied. If you apply, what happens? Behavior of this circuit is unpredictable. So that means the output could be either 0 or 1, so we cannot predict the output. We don't like this type of behavior in circuits. Unstable, that is. Sometimes it is called unstable state. So this is the state table. State table. As you know, memory elements is the simplest sequential circuits. There were three models. One of them, that was the state table, so that's the state table. This is the mathematical model. Since there is no an independent Z output function, our output here is just the next state dependent variable. So it is written next state function is this. There is no Z output function. So just one equation we've got here. And this is the mathematical model. And this is the state diagram, third modeling. So let me explain, say something about this definition relation here for this SR type memory element. How we are going to memorize it? Easy to memorize. 1, 1 forbidden. You've got to memorize that. If the input is 0, 0, what it says, this column, that means your state is not changing. If your present state 0, next state 0. If present state 1, next state is 1. So in short, we can say that for the 0, 0 input, there is no change in the state. So if you look at when that is forbidden. So what is left? S and R values, different cases. So this column, make it different color, or this column. So we can say that these two columns, if the inputs are different from each other. If it is so, if you look at this one, S value is independent from the present state value, make the output 0, isn't it? So that means S value is the same as the next state value. So we can say that in here it is whatever the S value is seen here. If they are different, whatever the S value is seen here. So how I can explain this too? You can say that if the input values are different from each other, that means column 2 and column 4. If the input values are different from each other, then next state values is the same as S values. So you can memorize it. You could transfer this state table to a state diagram like that. I will show you just one row here, so you can check your own the second row. So look at this row now. Present state 0, that means this. Make it different color, maybe it is better. So that's blue. That's present state. If you apply 0, 0, your next state is 0. If you apply 0, 0, your next state is 0. So I show you this. That is the one. So if your present state 0, if you apply 0, 1, your next state is 0. Your present state 0, if you apply 0, 1, your next state is the same as your present state. So that is the second one here. Now, if your present state is 0, if you apply 1, 0, so that is the case. Present state is 0, you applied 1, 0, your next state is 1. Present state goes to next state 1 when you apply input 1. So that one here inside is this one. That is the input, is this one. That is the present state, is this one. Okay. Now this is the definition relation. Why it is like that? Somebody says that this is an element that I produce. The behavior of this element, so that means input-output relation of this element as a definition relation is this. There's no reason for that. But what they say afterwards, the producer says that inside of that box, I put those two elements and connected them like that. So we've got to show now how the behavior of a combinational circuit gives you that definition relation. If it is so, I'm going to say that that's fundamental memory element is composed from those two NOR gates. So you might say that these are NOR gates, so this is a combination circuit. It is not a combination circuit because of this feedback here. So the output of this NOR gate is connected to the input of another one. So another feedback here. So on the other hand, I can say how I can say that this is not a combination circuit by sequential circuit. Look at here this column. Maybe clear this array a bit. So the input is 0, 0 here, but the output is 0 or 1. So that means for the same input, you do not get the same output. So it is not a combination circuit. So output could be either 0 or 1. So you need an additional variable in order to determine the output uniquely. That additional variable is that state variable. Okay, that's why it is not a combination circuit, but a sequential circuit, that combinational element. So I transfer the same circuit here. Now I'm going to analyze this feedback included combinational circuit, how it is turned to that definition relation here. So how I'm going to do it? So it says this is y and y prime. So we don't know this output is the complement of the other one. Therefore, I'm going to give different variables for that. Let's assume that this is t and v. So small t and v represent before I applied any input, and capital T and V is the next state. So this is small y represents small y, and this is capital Y. Why I put different variable names here, T and V, because I don't know when this is y, that's y prime. That's why I put T and V here. So in this case, T is going to be another, that is T input, and that's going to be the V output, V small v. So, and look for the capital Y, what's going to be. So these are the question marks. So I am trying to show that this circuit behavior is the same as this table described. So if I look at this table, it says to me that never apply 1, 1. I know that information, forbidden. Now, since I have got now 1, 2, 3, 4 independent variables, so I put those independent variables here, and the 16 inputs that is possible to apply to that, and that T and capital T and V is my output. That means next state. So let's examine the first one here. So this one. It says T, V, S, R, all of them 0. So that is 0, that is 0, that is 0, and that is 0. When this 2 is 0, 0 plus 0 gives you 0, prime of it gives you 1. When this is 1, 1 plus 0 gives you 1, prime of it gives you 0. Now I am saying there is an alternative to this. I said 0 plus 0, that becomes 1. But if the delay of this is longer than this one, so this also has got 0, 0 input. If you say that this NOR gate delay is less, then you're going to observe that one here earlier than this one. So if you observe here 1, that's the alternative, then that's going to be 1. 1 plus 0 gives you 1, prime of it gives you 0. So if this NOR gate delay is less than this one, instead of observing that 0, 1 here, I'm going to observe that green 1, 0. So that means depend on the delay of these NOR gates. At the output, I could observe either 0, 1 or 1, 0. So this is a problem case. For the same input, the behavior of this circuit changes. It might be 0, 1 or 1, 0. So that's a question mark. Just keep that question mark for a while. So in here there is another problem case input here. The output could be either 0 and 1, 0. This is another problem area. So you can examine this problem area your own and find that the output becomes either 0 or 1. So I left it to you. So I gave one example and left it another example to you to do. So I am going to write, I'm going to examine now another line here and leave the other lines calculation or findings to you. So let's examine now, or make it different color and make it blue. Let's examine this one here, this line. So it says T and V0. So T0, V0, and S is 1, S is 1, and R is 0, R is 0. What would be the output? So that means capital T and capital V. So 0, 0 gives you 0 plus 0 gives you 0, prime of it gives you 1. This becomes 1. Whatever this value is, because of that 1, that's going to be 0, isn't it? So this is independent from the delay, whether this delay is less or this delay is less, you observe always 1, 0. Because whether this value is 0 or 1 do not affect this output because of this 1. So I can say definitely capital T and capital V values are 1, 0 consequently. So if you examine all the other inputs, you're going to find this table. So I left it to you to find out the output for the other inputs. How many? 13 inputs, so you're going to do it your own. So let's look at this table under the condition that this input is forbidden. So if I transfer this information to that table, what I am going to see is this. S and R, both of them 0, is this case, or this case, or this case, or this case. There are 4 lines, rows, for which S and R inputs has got 1, 1 value. And it says forbidden, so I'm going to never apply those two 1, 1 inputs to this circuit. So if you look at now, examine the outputs. So that is 0, 0, and that is 0, 0, that is 0, 0, and that is 0, 0. What does this mean? If I do not apply that S and R values 1, 1, never apply these inputs, so I'm going to never observe that T and V values has got 0, 0 values. So that means the small t and small v, so these two, both of them 0, never happens. So that means this never happens, right? So that means I'm not going to observe this 1, 1 at all. So in this table, these lines, the red colored lines, never to be observed. On the other hand, if you look at the outputs, both t and v values never becomes 1, 1. So that means I'm not going to apply the small t and small v values as 1, 1. So this area is also another area which cannot be observed at all. So what is left is this area that is observable, and then is another area which is observable. So I wrote those two in here, those two groups in here. So if you look at this one, this table is the same as this definition relation. Why is that? Look at this here. Another thing that I've got to explain now, if you look at t and v values here, is the opposite to each other, isn't it? So that means I do not need that independent variable. This is a dependent variable, and this is the prime of this one. So I can share now this t is the this v is the complement of t, isn't it? So that means I forget that I show that this became complement. This output is the complement of this output. So I remove that. So what is left is that t. T is the small y. So I'm going to show this one is the capital Y. Small y is equal to 0 is that row. For this row, it says now if your input is 0, 0, so that means this, your capital Y, forget that because that is, sorry, that's going to capital Y, isn't it? I choose that T, so next state is going to be capital V. So clear this here and say that I have chosen T here, so forget that T, I'm going to observe capital T. So present state is 0, so that is 0. And apply 0, 0, this one. The next state is 0, so that's the capital Y is 0, so that's this 0. So I change the color now to blue. Present state is 0, that is 0, so that means that is 0, present state. And apply input 0, 1, applied input 0, 1. Your next state is 0, that's your next state is 0. Change the color one more. So when the present state is 0, that means that is 0. And input is 1, 0. Input is 1, 0. Your next state is 1. Your next state is 1. Input 1, 0. Next state is 1. So I show you that these three lines is this. I already accepted that 1, 1 is forbidden input. So this line is the same as the first group here, and the second line, you check it, is the same as this line. So conclusion is this. If I put in a box this circuit inside that, now I can say that R and R, that is SR memory element. So we show that that is the analysis of this circuit which tells us this circuit behaves as this table says, so as this definition relation. So the second fundamental memory element, this NAND type of fundamental memory element, to separate this one from the NOR type fundamental memory element, we put that stars here, S star, R star. So if you do this similar explanation that as we done it for the NOR gates, you're going to end up with this definition relation. So what's the difference this definition relation with the other one? So in the previous one, 1, 1 was the forbidden input. Now this is forbidden input. And when both of them 1, 1, state do not change. Present state is 0, 1. Your next state is 0, 1. No change. No change. When the inputs are different from each other, that means S star and R star values are different from each other. So in this case, R star input is the same as the output. So R star is 1 here, and output for this input is 1. When they are different, I said the values, R star value is going to be observed at the output. So that's going to be that's 0 and that's 0. Okay, this is NAND type fundamental memory element. Why we call it fundamental memory element? We're going to see later on that all the other memory elements are produced from these fundamental memory elements. So that is end of this video then.